Hello, my name is Paul Kigaya, and this is my whiteboard video for my 2023 City of Lights internship at Université Paris-Saclay. I worked on advanced optimization of laser wake field acceleration, supervised by Brigitte Cross and Francesco Massimo. Laser wake field acceleration is a technique that uses an intense laser pulse in the plasma to create a longitudinal plasma wave, which then can be used to accelerate particles such as electrons to extremely high energies over a very short distance. This is a numerical model of laser wake field acceleration depicting a white electron bunch in a blue plasma wave created by a yellow laser pulse. In order to optimize the electron beam produced by a simulation of laser wake field acceleration, we use the particle and cell method. This method uses a numerical process to solve problems involving the motion of charged particles, our electrons, inside a continuous electromagnetic field, our plasma. The method treats the physical domain, our plasma, as a moving grid with each cell of particles, our electrons, being represented as one point on the grid. The algorithm works by pushing the particles, accumulating the field effects, updating the current fields, and then interpolating them. This process continues over and over until a set number of iterations is reached. Here is an example of a technique that uses the particle and cell method. As you can see, after each iteration, the optimum is updated until reaching the specified number of loops. Many iterations are important to gather data. 3 techniques we used this summer were random scan, particle swarm optimization, and Bayesian optimization, which are all based on the particle and cell method. Due to the computation of our simulation using multiple parameters, derivative-free techniques such as these help optimize the process. My favorite technique this summer was Bayesian optimization. Bayesian optimization is a type of numerical computational method based on Bayes' theorem used to optimize black box functions, which are functions that are observed entirely based on their input and output. The general parameters for this technique set by the user were the number of samples or particles collected from each iteration, the number of iterations or loops, and the number of dimensions. The other 2 parameters set by the algorithm within the user-given intervals were the bunch charge, the charge at which our electrons were inserted, and the delay, the length at which our electrons are inserted after the laser pulse. The process is initiated by inputting the multiple parameters, observing the data points or outputs, building a surrogate model, maximizing the acquisition function, sampling the next point, and adding the new point to the dataset. This is done over and over until a set number of iterations is reached. The purpose of our research was to discover at what bunch charge and delay we achieved an optimal electron beam with a high energy and low variation between particles. The optimal points found were 948 megaelectron volts at 19.5 microns and 30.4 picocoulombs by random scan, 1008 megaelectron volts at 19.8 microns and 31.1 picocoulombs by particle swarm, at 914 megaelectron volts at 16.4 microns and 29.2 picocoulombs by Bayesian optimization. To further optimize our process, we used an unknown function named delta. The higher the value of this function, the better our electron beam, because a high value would be the result of a low deviation between the particle's energies, a high bunch charge, and a high median energy. The smaller the width and the higher the peak of these figures, the better, as this would be the result of a more uniform electron beam. In conclusion, due to the randomness involved in producing these results, multiple simulations will need to be run in order to compare their optimization histories and obtain a concrete optimal.